I'll say from my specific model of origins and ancestry in general, I have a very basic and testable definition of kind. I think you've heard it before, Mr. Anderson. And so my definition of kind is groups of organisms that can be traced back to a common ancestor. And so from that definition, now that common ancestor has to be independent and separate from other ancestors that other groups would descend from. Okay. And so an example of that is humans. So here on this basic phylogeny, why I think that's the best definition of kind, excuse me, is because it's testable. And so I can say, okay, humans today go back to a common ancestor, including your extinct humans like Neanderthals, Floresiensis, Naledi, so on and so forth. And that original ancestor would be separate, as you can see here on this phylogeny, to your chimpanzee group, your orangutan group, your Australopithecine, so on and so forth. Mr. Anderson, what are your thoughts on that definition?
I hate it, but just a moment. I just have to tell my wife I'm still alive.
She's like, I haven't heard from you in 3 hours. You still debating those young Earth creationists?
Well, he already lost. He already admitted defeat. He admitted there is no transition. So I don't know why he's still debating for evolution when he already admitted there is no evolution. He knows transition was required for evolution.
A specific example of exactly what kind of pointer trends.
Look, I can ask this question applied to bulls or butterflies. You're not going to come up with any answer.
I'm never going to come up with an answer that satisfies you, sir. I agree with that.
Satisfy me. Look, what you provided as an answer was the classifications. Classifications are made up terms that don't exist.
Well, I'm going to jump in because I've been waiting now about an hour. I want to engage Mr. Anderson for a little bit.
Yeah. No,
actually, and 2 hours prior to that with the Ken Hovind debate. And
That's right. So the answer to your question is I hate that definition.
Well, you shouldn't hate it.
I do, but I don't hate you. I don't like the definition, and the reason is I think that the reason is because I think that it's self-referential. So it's the same problem. It's actually very similar to the definition that T-Rock was putting forward. And the problem is that if we're debating ancestry, and you're saying that kinds is through the lens of kinds, and you're saying that kinds is defined by ancestry.
Well, it's because the Bible, so our starting position, maybe not Bubbles, T-Rock, our starting position is the book of Genesis. And the book of Genesis claims to be, the Bible, as a matter of fact, claims to be the history book of the universe. And so from that starting point, we should be able to test its claims of origins. And what the Bible claims is that Adam and Eve were created as the first couple, our first parents, and they were created and designed independent and separate from any other form of life, including what you would say is our closest cousin, the chimpanzee. And so from there, we can derive a testable definition, groups of organisms that go back to a common ancestor. That entire group would be separate from any other group, including your chimpanzee kind, you could say. And we can test that using scientific data. Go ahead, Mr. Anderson.
Yeah, maybe I don't hate this as much as I originally thought. So what you're saying, because what you're doing, which is a little different than what T-Rock was doing, is that you're saying, look, I'm going to give you the original ancestors that I say all of the kinds trace back to. So when I say, you can say like, look, a kind is anything that was descended from X and Y and Z, and these are the kinds, and here they are. That's what you're saying,
right? So, for example,
I can live with that.
Well, and I can only group together organisms that we know exist. So, for example, we have fossils of Neanderthals, Naledi, Hobbit. For many reasons, I would say that they are all human, and they essentially descend from Adam and Eve. And so, if I can show that extant humans today, right here, living humans, and all of your extinct human types go back to a single common ancestor, which I believe through mitochondrial DNA and Y chromosome specifically, which we can discuss. We have demonstrated that. And then that this original couple exists separately from your chimpanzee archetype, your orangutan archetype, so on and so forth. Then you have a legit created kind there, a special creation, which in a way answers the famous phylogeny challenge that Aaron Ra poses. Absolutely.
Can you do that? Because, like, I mean, well, you know, I don't mean to, like, I'm not trying to, you know, start a fight or anything. Like,
how dare you?
What I'm saying is that
well, you did say you're a meanie.
I am. Well, I was pretty mean to Kent.
When you're looking all your kid, I'm just kidding. I think you're a good sport. Well, let me. Okay, you know what?
Let me just finish what I was saying was that, like, if you, I'll just go back to that slide because I was looking at it.
Okay.
So if you were to say, like, okay, well, look, we can trace back the last common ancestor of all living humans, and therefore that's a created kind. Like, I mean, if you use that exact same methodology and then you included chimps,
right,
you can trace back the last. It does work.
No, it wouldn't work, because once we start looking at the best genetic markers, the best genetic way to determine and answer this question of ancestry, like your uniparentally inherited DNA compartments, Y chromosome, mitochondrial DNA.
Better.
Once you, it is better because they lack recombination, and so it's less messy. Oh, you said you did agree that they're better?
No, I don't. No, I don't agree. You're right. It is less messy, but it doesn't mean it's better.
Yep. No, because we can have an unbroken line within the Y chromosome family tree and the mitochondrial DNA family tree, because every generation that mutations accumulate, a new branch on the family tree is added. And so all you got to do is take those branches back to an original point. And using Y chromosome, using mitochondrial DNA, when you bring in the chimpanzee, you find that the mitochondrial DNA and also the Y chromosome is nothing like your human Y chromosome and mitochondrial DNA. And that includes extinct human groups that we have their DNA for, like Neanderthals, for example.
So here's kind of the thing. Why is that better than using, say, I don't know, one of the genes on chromosome 4?
Well, we could use orphan genes. Are you familiar with
I know what orphan genes are, but I'm not talking about using orphan genes, because that would by definition mean that you're not going to get outside of humans, right?
Well, exactly. It's a problem.
I don't want to use
it's a problem for the evolutionist model, because we have
that's a problem with doing something.
I'm almost done. For the audience sake, orphan genes.
Come on. Like that, if you use orphan genes, just so for everybody who's watching, orphan genes are genes which are unique to a species. So if you were to be like, well, let's compare orphan genes with another species, like by definition, if you choose orphan genes, they are not in the other species, right? So
we have orphan genes within
just
humans.
choose like chromosome 4, right? Chromosome 5, chromosome 1. Don't use chromosome 2 because that one's, split.
So, chromosome 2, but Bubbles, I'm engaging Mr. Anderson. Chromosome 2 would be another line of evidence for the fact that humans and chimpanzees are not related, because humans have 46 chromosomes, chimpanzees have 48, and we have strong evidence against a chromosome fusion in the past, which we can engage.
I don't know that. I don't know enough about chromosome 2 fusion to engage with you on that. I don't want.
Okay, well, I want to bring up one point for us to engage. Okay, we've actually discovered Eve. She's published in the technical literature, and so you can look up this.
Eve. I'm familiar.
Right, so you can look up mitochondrial diversity within modern human populations. This was published by Dr. Rob Carter, and so they discovered Eve's sequence. It's the consensus sequence,
and mitochondrial Eve,
right. And so it turns out that on average, as you can see here, on average differed from, so these sequences, any two people essentially on the planet in their mitochondrial DNA differ by only roughly 21, somewhere between 21 and 25 DNA differences or mutations from the Eve consensus sequence. And that is trivial to accumulate. It's very few differences in the overall scheme of things. It's biblical time. And so we have Eve's sequence, mitochondrial Eve. And
Mitochondrial Eve, yeah. Mitochondrial Eve, yeah. That's right.
So do you agree that based on this paper, we know her sequence, her original sequence?
Who, Mitochondrial Eve? You know Mitochondrial Eve's mitochondrial sequence, right?
Yes.
But mitochondrial Eve is not Eve.
It is, because they've discovered that. So notice this, based on the current data set, over 84% of the mitochondrial genome is invariant. And so most of it's the same worldwide. There's low diversity, low variation. There's only a few DNA differences separating any two people. The mutation rate in the mitochondrial DNA is somewhere between 0.1 and 0.5 per generation. And so just very basic math tells you that it takes really just a couple hundred generations max to accumulate an average of 20 to 25 DNA differences. But yet you would want to place mitochondrial Eve in Africa somewhere between 150 and 200,000 years ago. But the genetic data does not suggest that. You'd have to infer that. And it's a weak
inference. The genetic data doesn't suggest that.
Well, because I just pointed out right here, the mitochondrial DNA worldwide is incredibly invariant. 84% of it's the same. There's only a few DNA differences separating any two people. And so
that's the average, not the maximum. You have to use the maximum.
Right. And the max is only about 140. Right. And so still trivial in light of the mutation.
If you do a coalescence analysis, you get what is it, 100 to 200,000 years?
No, because that's not based on the observed mutation rate. That would be
it's based on the substitution rate.
Right. But here's the problem. Right. In your model, you understand that when it comes to an equilibrium point, because you have deep time scales, you have a per generation mutation rate, let's say 0.1 to 0.5, neutral mutation rate in the mitochondrial DNA that actually equals your long-term substitution rate. And so it really doesn't help you to look to the substitution rate. You still have to deal with the low variation, and you have to deal with the fast mutation rate.
No, the substitution rate is the substitution rate. It can be directly measured. I know Dr. Dan's been over this with you more than one time.
Yeah, but he's not a population geneticist. He doesn't understand the fact that in evolutionary timescales, Mr. Anderson, there's what's called fixation equilibrium. And so your per generation,
right? Yeah. Go ahead.
Okay. So your per generation mutation rate, if it's 0.1 or 0.5, like I said, that equals the long-term mutation rate, the substitution rate.
So first of all, Dr. Dan is an evolutionary biologist.
Right, but he's not a population geneticist.
Well, then talk to Zach Hancock, and he'll tell you the same thing.
Well, basic population genetics would tell us exactly what I'm saying. I mean, I can pull up.
You're talking about the molecular clock under like some idealized assumptions. So those idealized assumptions don't really hold, right? There's more complicated models. Like you're just using what, 4NE?
Well, it's the basis for
the basis for the molecular clock. Yeah, it's the basis for it.
So I want to pull up the quotes.
Yeah, that's the basics. But then if you want to get to actually like using the molecular clock to
right here, I found the slide. Since on average it'll take 4NE generations for such mutations to reach fixation, about the same number of neutral mutations should be fixed every generation. And this is in many ways a solution to Haldane's dilemma, because in light of the mutation rate, how long does it take in restricted populations for these beneficial mutations to basically reach fixation? Because you need not individual change, but you need species-wide change for forward evolution to take place. And in order for that to take place, you need beneficial mutations to reach fixation to the point where they're stuck in place. And that can drive forward evolution. But there's a waiting time problem that Haldane discovered.
I'm familiar with the waiting time problem, and we know why. Like Haldane's dilemma was solved back. I can't remember off the top of my head what the solution is to Haldane's dilemma, but I know What I do
partly
remember is
genetic drift.
It could have been, yeah. I can't remember.
Partly genetic drift, and that's why this is so important, and that's why Fatuma here says.
Here's an interesting thing that I did want to get into with you. Which is kind of related to this. Drill me on genetic entropy and your argument as to why genetic entropy is inevitable.
Hey, real quick, guys, and this directly leads into genetic entropy anyway, but I want to point out something about fixation. So fixation in the evolutionary model is always about populations, and so it's scalable from small to large populations, and the larger the population, effectively, the longer fixation takes. But here's my observation. I am willing to bet, and I'll gladly grant my ignorance on some of this, but I am willing to bet that you cannot demonstrate through actual empirical science that any given mutation actually fixes in a large population. In other words, it's entirely hypothetical.
Well, in young Earth creation timescales, we don't really believe in population-wide fixation. We've only got 4,500 years, and so we don't have fixation equilibrium, especially after the Tower of Babel, when people spread out to all parts of the globe. You might have localized fixation, but not population-wide fixation.
Yeah, that's exactly the implication, is that the population is much more likely to diverge and split apart than it is to linger around long enough for the mutation to fixate. And if that's true, it basically blows evolution out of the water, because it has to have the time for the fixation to occur.
The evolutionary model
you can calculate the time to fixation, and I don't remember exactly what the formula is, but it is a pretty long time.
You can calculate it, but you can't demonstrate it. That was my original.
Well, you can demonstrate it in creatures that have shorter lifespans, and then you're going to have to assume that the laws, like you're going to have to assume that the relationship holds, and if there isn't something that we don't know about, which makes humans different.
Gentlemen,
we don't know of anything that would make it different, but I mean, yeah, it's an assumption.
I want to point out something really important real quick before we move on. So this paper, and we can get to genetic entropy for sure. That's one of the lines of evidence, separate from the Eve consensus sequence. But the author of the Eve consensus sequence paper that we were just talking about, Mr. Anderson. So right here, Dr. Rob Carter, and Dr. John Sanford, they both worked on this. Well, the author here has responded himself to the same claim that you made, that Dr. Dan Stern-Cardinal made. And right here, Rob Carter says this is referring to Dan Cardinal, claims I misunderstand the substitution rate versus the mutation rate. Yeah. And he has said, similar to what Chris Roop and I have written about, I am perfectly well aware that the long-term substitution rate is not the same as the genealogical mutation rate. However, over long periods of time, right? So here's the fixation equilibrium that you understand.
What do you mean by fixation? I don't think you're using that word correctly. Do you mean mutation drift equilibrium?
Mutation drift equilibrium, I think in many ways applies to mutations, beneficial mutations.
No, mutation drift equilibrium is the concept that when you have a population which has reached a local peak of fitness, that mutations are going to introduce, that most mutations are at that point going to be deleterious, and mutation is going to introduce variation, and then
more beneficial. There's going to be a counterbalance where now more beneficial mutations are accumulating than deleterious.
No.
Well, then explain yourself better, Mr. Anderson.
Yeah, no, I'm trying to. I'm trying to. Don't worry. I'm doing my best. I'm just not that bright. So at a localized peak, right? Like once you get, it's kind of like, when you hit the top, there's nowhere to go but down, right? So if if a creature reaches its maximal sort of level of fitness for a given environment, and that environment doesn't change, then most mutations that occur are going to be deleterious, just because there's nowhere to go but down, right? And so then it's going to introduce mutation, like mutation is going to introduce variation, and then selection is going to remove that mutation. And that's selection mutation equilibrium.
Yeah,
right?
so here's mutation drift equilibrium right here. Mutation drift equilibrium is a standard part of many evolutionary models. Given many millions of years, one would expect genomes to become saturated with mutations, reaching an equilibrium where the number of new mutations is balanced by the number of mutations lost through random drift and purifying selection. So it's not the same thing as fixation equilibrium that I'm talking about.
Well, yeah, okay. I don't know what this is, but I was talking about mutation selection equilibrium.
Okay.
But I don't know what this mutation drift equilibrium is then.
So
something
fixation equilibrium that Chris Roop and I have wrote about is simply the fact that over long evolutionary timescales, your per generation neutral mutation rate will equal the fixation rate. And so if 50 mutations are, if 50 mutations
for neutral mutations, right?
Neutral, yeah, of course, because
not for nearly neutral mutations.
Nearly neutral as well.
No,
because,
nearly neutral, you got to use a different formula.
No, because nearly neutral mutations are not subject to selection, and so they act as neutral to selection, but because they have only slightly deleterious effects, they still drift, and they would drift to fixation. That's genome-wide or population-wide genetic damage.
Just give me a sec. I gotta get my other book. No, that's not correct.
Take your time. I want to just finish reading Rob Carter's quote because I think it's pertinent to the fact that he's the one that wrote this paper on the Eve consensus sequence. And your rebuttal was, well, you got to look to the substitution rate. Well, the authors responded to that. And so he says, actually, I'm screen shared, so I can't even tell if you're still there. Let me check. Okay, he walked away. You know what? To be fair, we'll wait for him. So
Donnie, I have a question for you.
Sure, go ahead, brother.
So, and correct me if I'm wrong, but is it the idea that most creationists believe that evolution and the idea of evolution and the idea of the Big Bang aims to dismiss the idea of a God? Is that like the overarching theme? Because I don't personally believe that like Charles Darwin had the intention of being like, yeah, let me disprove God. I think he just observed some things and he had a misunderstanding. But just something that
I think it was Charles Lyell, but don't quote me on this. I think he's the one that said, as he worked in uniformitarian ideas, that we need to get away from Moses. We need to get away from flood geology. We need to essentially give it up. I can't remember the exact quote. It was something anti-Moses and anti the flood. So in many ways, yeah, uniformitarian and evolutionist thinking is at least a direct attack on Moses and Genesis and the Bible's account of origins. That's not to say there aren't Christians like at BioLogos that would say evolution is the means by which God brought forth the various life forms, right? But I do think the thinking originated out of a disliking of Genesis and its clear account of origins.
Okay, if we could explore that a little more after, I'd really like to. Thanks.
Hey, Donnie, sorry. Can I dive in real fast? Can I answer Josh's question real quick?
Sure, go ahead, yeah.
Josh, to answer your question, why evolutionists chose their belief system, if you look at history, in past history, starting from when this country was founded on biblical principles, our Constitution is founded on biblical principles. It's written, "We the people." It starts, "We the people," and then it goes on to say, and then even our anthem, our flag, national anthem. Sorry, Pledge of Allegiance says one nation under God. So Benjamin Franklin, George Washington, our founding fathers, they all had a biblical principle. They tried to put that into the country. But the reason why this slowly evolution started developing is because I believe evolutionists are trying to run away from accountability. Because God says, God gave us a law. And when you said Moses, God gave us the Ten Commandments, and afterwards Jesus gave us grace, but still we have rules to follow, and our conscience and the Holy Spirit works through the conscience. So I believe that a lot of evolutionists choose their belief system because they don't want to follow the principles or the laws that are given by God because it doesn't suit their lifestyle or it
Let's
doesn't suit their morals.
let's
Yeah,
explore
okay,
let's explore this a little
Well,
deeper.
guys, I'm gonna jump in. I don't want us to get too far off
Yeah, that's
track.
what I'm saying.
I want to
Let's
keep.
get back to the
I
subject.
appreciate. Don't worry, we're gonna have plenty
Yeah,
of
that's
time for
probably a
open
good
debate.
Sorry
call,
about that, Donny. Yeah,
Probably
thanks
a
so
No,
very-
much,
that's
guys.
okay. That's okay because Mr. Anderson stepped away for a bit. Anyways, you're back, Agent Smith. So let me just
Yeah.
finish my point. I know you got a book, so you'll have a point to make.
No,
But
it's
the
just
author-
notes. Go ahead.
Okay. So the author, Dr. Rob Carter, he says, however, over long periods of time in a population and mutation drift equilibrium, the two are nearly equal. There is also not, as he claims, a conflict between the thought that A, most mutations are lost to drift, and B, and this is what I point out, the mutation rate is approximately the same as the fixation rate. Why? Because even if most mutations are lost, in a large population, many are not. And Fatuma, he points out in this evolutionary textbook on PopGen that we're looking at, if you continue the quote, Mr. Anderson, and then I'll let you respond. If you continue the quote here, where he says the rate of fixation mutations is theoretically constant equals the mutation rate, the neutral mutation rate, he begins to talk about population size. And he says population size is not going to affect this because in a large population, fixation's slower, but you have many more mutations entering the population and spreading throughout the population. In a small population, you have less mutations entering the population and spreading throughout the population because less individuals, but you have faster rates of fixation. And so there's a counterbalance there where this rule essentially still applies. Go ahead, Mr. Anderson.
Yeah, I agree with that. For neutral for neutral mutations, that's true. The problem occurs when you are trying to use nearly neutral mutations, because when you do that, it's different, right? And the reason it's different is because with neutral mutations, like that's correct, right? The more people you have, the longer the longer it's going to take to spread out across the population. But by the same token, the more neutral mutations there will be, right? With a nearly neutral mutation, it's a little bit different because the question then becomes, how nearly neutral is it, right? Because not all nearly neutral mutations are created equal. And a nearly neutral mutation is a mutation which is close enough to being neutral that evolution, or selection, I should say, doesn't see it. And it's going to not see it depending on how many times it gets a look at it, right? And that is going to depend on two things. The first one is, how bad is it, right? How nearly neutral is it? And the second one is population size. And there's two ways to calculate population size, right? There's effective population size, and then there's like how many people are there, right? So the formula is that the probability of fixation of a nearly neutral mutation is not just equal to the mutation rate. It is 2Ne over N all over 1 minus e to the negative 4Ne times S, right? So it's just a much more complicated formula, right? And that's the basis for for every mutation that you do or that you want to calculate, it's going to depend A, on population size, and B, on how nearly neutral is the mutation, right? So what's going to end up happening is that some of these mutations are like, the closer it is to neutral, the more likely it is to get to fixation, right? And the smaller the population size, the less close to neutral it has to be before it's got a pretty good probability of reaching fixation. So the really bad mutations never reach fixation.
Well, the really bad mutations would be subject to selection, and that's the whole point. Is you're trying to make the no selection zone in terms of these neutral mutations. You're trying to make it as small as possible. When in reality, I didn't interrupt you. Let me just finish. If you disagree, just note it down like a debater does, and you can respond to it. The problem is there's so much in terms of genetic noise. There's selection interference where you have all these traits segregating in the population that your most beneficial ones are just never even amplified because of the noise. There's so much going on in the genome that what you're arguing seems to me to be very one-dimensional and counter to what a lot of these evolutionary scientists in the field are saying. Like right here, Iyer, Walker, and Keatley, they say it seems unlikely that any mutation is truly neutral in the sense that it has no effect on fitness. And so where you say, and this is where I'd like you to speak, it sounds like you're agreeing that, okay, the same number of neutral mutations should be fixed every generation. The rate of fixation mutations is theoretically constant, equals the neutral mutation rate. So you're saying this does not apply to the nearly neutral or effectively neutral mutations, though. Is that what you're saying, Mr. Anderson?
Yeah, that's right. Because for effectively neutral or nearly neutral, that depends. And it depends on how nearly neutral they are, A, and B, it depends on what's your population size. So let's say and here's kind of the problem, as I understand it, with like the genetic entropy model, is that, let's say, for example, that you've got a mutation which is nearly neutral, right? And it's spreading across the population and it's drifting towards fixation because it is within that no selection zone on its own, right? Like a time bomb, right? And then you've got your trigger, right? So it's like this mutation and that mutation on their own, they're neutral. There's no fitness cost, right? But together there is, right? Then what that means is that they're never going to both reach fixation, because whenever, let's say one of them reaches fixation first and everybody's got it, right? That means then that if it is deleterious, if it has an effect on fitness, and fitness, I'm defining fitness in the conventional sense, right?
Reproductive.
If it has an effect on fitness, then it'll have an effect on fitness, which means selection will see it and it'll be subject to purifying selection, right? It'll never reach fixation because its value of S gets bumped up, which screws up the whole formula.
See, the issue that I have is I believe you are underappreciating the just how nearly neutral even these neutral mutations are. Because like the quote from Iyer, Walker, and Keatley, they said no mutation should be truly neutral in the sense that it has no effect on fitness at all. And so I would argue that yes, even your strictly neutral mutations, if you want to call them that, they're still going to be slightly deleterious in the same way that a single rust molecule, you've heard this, on a vehicle is deleterious, but it's not going to destroy the car. It's the accumulating damage over time, or a single spelling mistake in a book the size of an encyclopedia. On its own, it's inconsequential, but as enough spelling mistakes accumulate over time, the message becomes muddled and the book becomes unreadable. And just like the genome, this is a ticking time bomb. I do think that the reproductive way of defining fitness is greatly flawed, because by the time the entire
let's not get into that. Just give me that one. We can talk about that later.
Well, I'll ask a clarifying question. So you have two neutral mutations, nearly neutral mutations, entering the population. Depending on the size of the population, it sounded like you said, okay, maybe one is strictly neutral, but then another one has an effect on that one that makes them both seen, and so selection removes them from the equation. Or did I misunderstand?
Selection would only remove the second one, probably. Right?
Okay. And then the other one would.
This is an example of what they call mutational load, right? So like you've said, like on many occasions, we're all multiply mutant, right? And so we do have these deleterious mutations that are often heterozygous and recessive, right? And when they hit homozygosity in a particular person, then like the time bomb goes off essentially, and there's a big problem, right? Or even there's a little problem, right? But so here's part of the thing is that, I'm sorry for diverting on this. Actually, I'll finish that thought and then I'll go on to this other one. So what that means then is, let's just use the example of the big problem, but it's only a big problem if there's an accumulation, right? So at the point where there's enough of an accumulation of rust spots, for example, in the car, where it does have an effect on fitness, then that last mutation, which would actually cause a selection effect, is never going to reach fixation. Because as soon as it hits, as it starts to spread through the population, if those other things are already fixed, and now this is going to be the straw that breaks the camel's back, the straw that breaks the camel's back will never reach fixation because it is selectable. Does that make sense?
Okay, those are some good points, interesting points. This is technical for sure. And I would recommend that you and I do our own just 2-hour show where we can discuss this for sure. And so I think that'd be fun. And I do appreciate your professional approach to engaging this, Mr. Anderson. And so I would argue that fixation only exacerbates the problem. Okay, so any mutation that reaches fixation, if it is slightly deleterious, that is very small damage population-wide, where now it's not subject to selection because the entire population has that mutation now stuck in place. I think we'd agree with that. But genetic entropy still applies when mutations don't drift to fixation, because let's say, for example, in the human population today, we got about 7 to 8 billion people. Mutation rates about 100 per person per generation. That's 700 billion new mutations this generation alone. And so those mutations will spread. They will lead slowly into genetic sickness. And by the time selection can see the damage, as you pointed out, everybody's multiply mutant. And so all it can ever do is slow down the genetic degeneration problem, because let's say we invoked really strong, intense selection, removed 50% of the worst mutants. So let's say you remove 4 billion people. Well, what are you left with? You're left with 4 billion people who are more mutant than the generation before it. Here's the last thing I'll say, because the whole point of genetic entropy is that every generation is more mutant than the previous generation. I'm more mutant than my parents. My parents are more mutant than their parents, and so on and so forth. Go ahead.
I don't think that's quite right. Like, the thing is that, so you are correct that there is such a thing that we call, like, I think it's called mutation load, right? Where we are all multiply mutant, right? But what happens is that instead of it being like a straight line that just continues to go up and up forever, what happens is that, like, there's a point, like what you're calling like the meltdown point, and portions of the population are going to hit that meltdown point before it fixes, and then they're going to suffer those effects, and then that, what I'm calling the straw that breaks the camel's back, gets eliminated. Now all the other straw that's on that camel's back still there, and that's what they call the mutational load. And it's a thing, and it does cause us problems. And like, that's why, like, they say, like, women have, I think, like 2.5 births per woman or something like that. That's actually not quite correct. Like, women have more than that, because you're not counting all of the miscarriages that occur, many of which they don't even know about because they're aborted very early. Right. And that's because of the mutation load. And so it's a mutation load that we can and do bear because there's not a significant amount of investment in the fetus when the woman's body detects that we hit the reverse genetic lottery and we need to.
Wouldn't that be considered one of those big mutations that results in no reproduction? If it's a mutation in the zygote or the growing baby in the womb, well, that baby is not going to be born, and then there's going to be no reproduction. And so,
it's like I said, it depends. Like, a lot of these mutations, these like slightly deleterious mutations, are recessive, right? And a lot of times, like, they don't have any effect at all until or unless more than one of them is in the same person at the same time, not just homozygous, but like homozygous, in multiple spots. And then sometimes,
and that's the problem is, as you know, I don't want to respond to that just yet because I want to respond to what you said first. My rebuttal to what you're saying is, yes, I agree. There's fitness variation. Okay, so everybody's multiply mutant, but some might be more mutant than the others, and so therefore those mutants can be removed from the equation before other mutants. But I would use an illustration to make it more understandable for the audience. Let's say you had a car lot and you had 350 cars. Over time, they're all accumulating damage. They're all accumulating rust molecules, but some, for whatever reason, they're going to accumulate more damage and more rust molecules. Like a GM's probably going to turn into trash before maybe a Honda or a Toyota. Okay, so the point is, sure, those are going to be removed from the equation first, but that doesn't mean your Hondas, your Toyotas, your Nissans aren't also going to be subject to that same damage through rust. And eventually they're going to be wiped out as well, to the point where that entire car lot is done. And that's the same thing with the human population. Is, yes, degeneration can be slowed. Some are more mutant than others, but all you ever get is a slowing of the degeneration process, because every generation is still going to be more mutant than the previous generation.
Yeah, no. So here's the problem with that idea, as I understand it. Again, I'm not a population geneticist, right? But my understanding is, like, so, you talk about, like, well, let's give like the example, your classic example of a deleterious mutation, or a slightly deleterious mutation that you would say does not affect fitness, right? So, the two examples I hear you give all the time are the Paul Price example, which is, he has asthma, and so his breathing is like slightly affected, but he can still have kids, right?
I kind of like the age one better, if you want to use
the age one.
Yeah.
Okay, so let's do the age one then. So the age one is that, like, look, there's this deleterious mutation, and it like reduces your lifespan by 2 years, right? So you would otherwise have lived until 70, but now you're only going to live until 68. And so the argument is that that's not going to affect your ability to have kids. It's just going to mean that you die sooner, which sucks for you, but it's not a mutation that evolution can see, right? Like, have I fairly represented your example?
Yeah, I think you're doing well. I would say, okay, you get a mutation that affects, like you said, let's say the lifespan by 2 years. And so I'm able to live to 70. And then my kids, because of that mutation they've inherited, now they're only able to live to 68. That's not going to stop them from being able to have really as many kids as possible. But then the next generation, they only live their maximum lifespan 66. But again, that's not going to stop them from being able to have kids.
Pause. So number one, we're way ahead of ourselves. So let's just talk about the first mutation.
Okay.
Where
the first generation.
Where you're saying, like, look, me living until I would otherwise have lived until 70. People live a range of of ages, right? But I would otherwise have lived till 70, but I'm only going to live till 68 now, because of this particular mutation. And the idea is, or the argument is, that is a mutation that selection cannot see, right?
Selection cannot see it. Because it has no effect immediately on reproduction, but one would be insane to say that it's not deleterious in some way.
Right. And the thing is that in population genetics, they would assign an S coefficient to that. And the reason that they would do that is because just because you've had your kids already doesn't mean that your life doesn't matter in the evolutionary sense. Because if I died 2 years earlier than I otherwise would, and that may mean that I can't be as good of a grandfather to my grandkids. And maybe that won't matter, but maybe it will. And it may not matter for me, and it might not matter for you, right? And it might not matter for, like 1,000 of the people that that this gene spreads to. But
Mr.
eventually,
Anderson, if I could, and I appreciate this, just so we can interact, using an illustration, yeah, I think that perfectly aligns with the example that I give about a single spelling mistake in a book the size of an encyclopedia, or a single rust molecule on a car, where it's inconsequential, just like this example right away. But if I were to go to that specific part of the book where that typographical error has been introduced, it might be just a little more difficult to read that word and therefore be able to understand that sentence prior to that spelling mistake being there. And so in this example, yeah, I think that's a great point you made, that although I can only live to 68 now instead of 70, well, that's 2 years taken off my life to hang out with my grandchildren, to be a blessing to them.
I'm more saying that like that could have an influence on your grandchild's survival, right? Like maybe having that grandfather there would have made a difference, right? And that's the measurable effect, right? And maybe
a lot of guesswork, though.
Yeah, well, it is, except how much do you know about like multiple linear regression?
Multiple linear regression. You'll have to define that or explain that.
Okay, it's no problem. It's a bunch of like math stuff. Basically, if you've got a large enough number of people and you've got a whole bunch of different factors which are affecting different things, and each one of those, individual people has a different set of things that are affecting them.
Okay.
Then you can do a bunch of math to sort of try and cancel out the different things that are affecting things. So it's kind of like if everybody's got all these things affecting them and we can regress all of those to the average, then we can figure out what the average is. And then we can figure out, but for this one thing that we care about, what would the line look like? And then what does it look like now? And they can actually measure the difference with respect to this one particular thing on a whole population. So even though evolution typically, well, let me finish.
Well, but I just want to make sure I'm understanding. So the regression is towards what?
Regression towards
a more average state, a better state.
Regression towards the mean is the statistical term.
Okay.
Yeah, you won't. I don't know if you want to look it up later, but the idea. I'm just trying to give you like a real big kind of basic rundown of this idea. So ultimately, what I'm saying is that although typically like evolution acts on phenotype and not like particular traits, if you have enough people, and it's gonna act on like that particular thing, right? So if you got enough people, you can isolate that particular thing that you care about, right? So I can actually have selection affect the 2 year thing, the 2 year difference, even though like for Paul, it probably didn't matter because he's got such a glorious mustache that he would have had a bazillion kids anyway.
But right? I do want to say that it still did not stop the individual who now can live to a maximum of 68 versus 70 from having 10 kids, from having 15 kids. They can still have as many kids as the previous generation.
I understand. Like I said, with the glorious mustache Paul has, he will have as many kids as he wants, right? But that may not be true. Like his grandkids might be fine, right? But if you look at it across a population, in terms of that sucker, reaching fixation, it has to hit beautiful mustaches every time, right? And as soon as it doesn't, then selection's going to see it and it gets eliminated.
Right, but it's only going to become a massive problem to reproduction and the overall health of the species' ability to reproduce and have lots of kids, differential reproduction. Once it reaches a point where the maximum lifespan is something like 30, 25, and so it's like a ticking time bomb where you have. I just want to say this, and then you can take your time because I got to run to the restroom real quick. I've been drinking a lot. So basically,
I don't want to talk to the air. I want to talk to you.
Well, no. I was going to say you can interact with the audience just for 30 seconds while I'm gone. So I want to make this point. You have a bomb, and it's set to go off in 3 minutes. Yeah. Well, that countdown although scary, because once it hits 0, the bomb's going to go off, and now we've got incredible damage, right? We've got an explosion. That explosion does not come until the timer hits 0. In the same way that these nearly neutral mutations can accumulate and eventually affect reproductive fitness, by the time it does affect reproductive fitness population wide, it's too late. The population itself has descended into complete genetic sickness, and there's no going back to good health for that population.
No, the reason that that's incorrect is because if it matters, it matters, and it affects selection. If it doesn't matter, it doesn't matter, and it doesn't affect selection. So like either it matters or it doesn't. And if it matters, it will never reach fixation. And if it doesn't matter, then it doesn't matter.
Okay. Put a pin in that. I will respond. I'll give somebody else on the panel the opportunity to bring up a point if they would like to. Josh, I think you just
unmuted. No, I'm like driving home. I'll be home like in 10 minutes, so I'm gonna really try to engage at that time. So T-Rock, I don't know if you want to take it from here for now. T-Rock,
I got a question.
Go ahead, Dan.
Mr. Anderson, don't you find it suspect that in 3.7 billion years ago, bacteria only evolved one time and only made one tree of life, and only some of that bacteria evolved and all the other bacteria didn't evolve for 3.7 billion years?
I would find that suspect, yeah.
Okay, so that's the beginning of your evolutionary tree. So,
well, no, I mean, that's so. Do you know? Okay, so coalescence theory, right, is that, says that like whenever if you go back far enough, we all can trace our ancestry back to a single ancestor, right? A single individual, just kind of by virtue of. There's a good video about this. I think it's either Dr. Dan or Zach Hancock has a good video about explaining why it is. It's Zach Hancock, and it's the video about Cheddar Man, and explains like how if you go back far enough, if an ancestor is an ancestor of any of us, he's gonna just mathematically certainly be an ancestor of all of us. But that does not mean that that was the only person around. And so by the same token, that one bacteria that we can all trace our ancestry back to was not the only bacteria around. It was a member of a population.
No, I know, but why
all of us are related to that one?
But why wouldn't bacteria continue to evolve like new trees of life for 3.7 billion years? Why wouldn't
they did?
Why did it? No, they didn't.
Yeah, man, they did.
That's not what the tree of life shows.
No, like, oh, so you're saying like why is it not the case that another bacteria didn't go off in another direction and that there's like a separate ancestry of like a new tree,
or something? Yeah, like, or
again, it's got to do with this mathematical concept of coalescence theory. So yeah, that's the answer is the answer is you should learn more about coalescence theory, and that'll answer that question.
Okay, thank you.
Okay, well, let's get back to what we were talking about there, Mr. Anderson. And this also goes back to what I was saying in terms of answering this question of ancestry, where I believe I can show why humans and everything associated with the humankind is unrelated and separate to any other form of life. I like sticking with the chimpanzee because you would agree that if evolution is true, chimpanzees and bonobos are our closest living relatives, as we share a common ancestor with them. And so why not stay as close to home as possible rather than showing you why, let's say, strawberries and humans aren't related, right? Let's stick with.
I've been down that road for like 2 hours already today, and then 2 hours already on another day. So sure, let's stick with.
Least I can do for you, since you're a good sport, Mr. Anderson, is stay as close to home as.
No, like I said, I do this because I enjoy the intellectual challenge, and Dr. Hovind is he's certainly wily,
Well, I want to make a point about what I see. I see you and your evolutionist friends, and feel free to push back on this, but I see you guys magically making the no selection zone unrealistically small to see every tiny mutation, basically to transition it from drift to selection midway through. That seems to be what you're saying, that at first they're unselectable, selection can't see them, but eventually they're going to amount to a point where now they are seen by selection. So it's gone from drift, they've been drifting, but now they reach a point where selection can see them.
Well, I mean, the thing is, so you were talking about there's going to be this genetic meltdown, right? Mm-hmm. What I'm saying is that point of genetic meltdown, that at that point, that change, which would otherwise cause the genetic meltdown, will never reach fixation, because genetic meltdown is a very deleterious thing. And so what'll happen is that you're going to hover right underneath that genetic meltdown point, and then parts of the population are going to go over it, and they're going to have that effect, whether that's a minor effect or a major effect, but let's assume it's a major, because genetic meltdown sounds like it's going to be pretty major, right?
Right.
So when part of the population accumulates that last little bit that, bam, we're in genetic meltdown, they will suffer that effect, and they'll get eliminated. And then everybody else is going to hover right under the line. And then somebody else, that mutation is going to happen somewhere, and they're going to go above the line. Genetic meltdown is going to happen for them. It's never going to fix. They'll die, and you'll go down again, right? It'll go like this. It'll go. And it just seems like right at that genetic meltdown. It's going to walk that line, and it'll do that forever.
It seems like hope, dream, and imagine, right? That whales and pine trees are related, because it just right. And that's the problem is there's a lot of unrealistic mathematical modeling going on here.
What's unrealistic?
Because take the example of humans today. You got 7 to 8 billion people on the planet. Yeah. Mutation rates about 100 per person per generation.
Sure.
And so population wide, we have a ton of mutations in the population. And so sure, get to a point where you reduce the population by 50%, the 50% worst mutants. Now you're left with, let's say, 4 billion people who are still more mutant than the previous generation. Okay, time goes on. And
they're more mutant than the previous generation, but not in the bad ways, right? Like, you've reduced the number of really deleterious mutations.
I would say yes, because
the new mutations that accumulate aren't necessarily going to be as bad as all of the ones that you've eliminated, right? So that's a big purifying event. Now everybody is less mutant than the previous generation. Now they can start getting more mutant again if you want, but then you're going to have if you have another big selective sweep like that.
No, but the people who remain, those 4 billion people, they're they've accumulated more mutations than their parents, than their grandparents. So that's what I mean. They're still more mutant than their previous generation, maybe not more mutant than the ones removed.
Right.
But eventually they're going to reach a point to where the ones were that were removed, right?
Right, that's right. We're gonna hit that thing. We're gonna go right. You're right that even after you go down, right? Like, let's say it goes up, and then now there's a bunch of people who are let's say, like you said, half the population, and they all die because for some very strange reason that could happen in a small population, right? Where because
more recessive mutations come to the forefront in a small population.
And it's easier that the glorious mustache can hide more mutations than right.
It's a nice beneficial mutation to grow.
If you're
I've been growing this. I've been growing this for 34 years.
But no, I mean, look, yeah.
Okay, let me say this.
So you and I get that asthma. We're our genes aren't making it to the next mutation. Paul Price, No problem, right?
So
Glorious.
shout out to our boy Paul. So we should set up a conversation, you and Paul. So let's say we have 2 lines. Okay, here's try and get in the camera. So everybody's accumulating mutations. Okay, so they're going up, 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 but then eventually this part of the population goes up a little further, and you're saying, "Oops, selection can see them; they're removed."
Yeah, if they hit that.
So now everybody's back. So now everybody's back to here.
Just barely under that line.
Okay,
that's
so
right.
now but then they're going to go up, 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 up.
It's some of them. Some of them are. Some of them are. Some of them are.
Okay, so let's see. If I had more hands, I'd be able to make it better.
Well, no, just say that. Like, look, here's a population. This is the total population in the world goes this way, right? Time goes this way, right? So as mutations go, the population continues to increase. We hit that meltdown point, increases a little more. Now people start to die. The population goes down.
And that's where I disagree. No, see, I don't agree that the population is going to start going down at that point. You're going to have you're going to have the worst. You're going to have the worst mutants removed, but the rest of the population is still. It's not like suddenly they're going to start going down.
No, the average number, like the average badness, right, in the genome goes down when you eliminate the outliers, right? Like if it's just mathematically, that's a fact, right? If you take the 50 dumbest students in a class and you murder them, then when you take the average test scores, they're going to be better, right?
Okay, they're going to be better, yeah. Okay, but
even though the other kids did not get any smarter, the average is up, right? So, and then they start getting dumber, right?
I'm not sure it's a 1-to-1 comparison though, because some students,
that's
they
a messed up
excel
comparison.
more because they're studying, they're doing their homework, they're putting more work into it rather than the slackers. But I find it interesting because if you do have selection so we have this issue that population geneticists in the past, the 50s, 60s, I think it was, they pointed out that we need forward evolution, which means we need fixation, specifically fixation of beneficial mutations. But fixations, it's so slow, for these beneficial mutations to arise, become fixed in order for population-wide change. And then genetic drifts introduced. Oh, most mutations are neutral, which means selection can't see them. And so they're not subject to selection. And so they'll be able to drift to fixation. And there you go. You've got forward change. But now, because of this problem,
no. Selection, positive selection, and drift are different, right? Like I know I can't remember exactly what the solution is to the Haldane's dilemma thing, but it's different than.
Well,
that is part of it,
but you need those neutral mutations to reach fixation for species-wide change, right? Yes or no?
Like positive selection is a much stronger force than drift, and it's a stronger force than purifying selection in a sense, right?
But if the majority of mutations are neutral, what's in effect more, drift or selection?
Depends on the population size.
A large population, 7 billion.
In a large population, then selection is going to have a greater effect on fixation than drift.
Okay, so if you have selection operating, then we've basically just undermined the basis of the molecular clock. So now you're going to have fewer of these mutations reaching fixation for evolutionary change.
Like because beneficial mutations are relatively rare, the most of the mutations that do reach fixation are still going to be neutral or nearly neutral.
But when a beneficial mutation becomes fixed, what else becomes fixed with it?
Well, you're talking about linkage blocks, right?
Your deleterious mutations are going to be fixed with it.
If you're going to evaluate like a beneficial mutation that's got strong linkage to deleterious mutation, I think you have to evaluate the linkage block as a whole, because you're going to have to take the good with the bad, right? Unless it's one that can be, sorted by recombination, but not all can, right?
And those deleterious mutations let's say you have a linkage block of 10,000 nucleotides. Well, the bad is linked with the good.
I don't even know I don't know how many alleles that would correspond with. I'm not that smart.
Well, let me ask you this then. I would argue that even when your beneficial mutation does arise, about 1 in a million, the Lenski experiment discovered.
Sure.
I would argue, I'm not saying all the time,
but be different, but yeah, whatever. We'll just take that as a number. Go ahead.
Go with that. 1 in a million. They turn out to be genotypically, not all of them, but most of them reductive. where they're still functionally compromising to organisms. And so now that is still deleterious in many ways, even though it's labeled a beneficial mutation. So that's just going to speed up.
Yeah,
Okay, I see you giving me a funny look.
we're-
I see you giving me a funny look. Okay, take sickle cell anemia. Genotypically,
okay.
what's happening on the? We understand what happens on the phenotype, right? If you have
Yeah.
sickle cell
Yeah.
anemia, you're resistant to malaria. Okay, that's phenotype. But why on the genotype? Why is that the case?
Why on the genotype?
Yeah.
I have no idea what the A, C, and T and G of.
Well,
I don't know what the code is.
So
do you mean like because the cells are a funny shape, and so like the
form,
malaria
yeah.
virus? Yeah. Okay. So you mean on the phenotype?
It's a well,
because the
genetic
phenotype
content.
is the expression of the genes, which makes the cells, moon
But
shape.
when we
right?
look at the genetic content of the individual who is
Yeah.
resistant to malaria, because we see outwardly, okay, this person is more resistant to malaria. They have sickle cell anemia, but the genetic content, why is that? You just said it's because they have a deformed hemoglobin protein, I think it is. And so basically it's due to a broken cell, broken protein. That's reductive.
Well, so here's kind of the problem, right? Is that like now we're getting into kind of a philosophical debate about whether or not like information is a thing.
Well, I didn't even say information. I didn't say.
Well, we're talking about whether or not something is beneficial or not, right? And whether or not it's reductive, right? Or
reductive has nothing to do with information, though. It just means the cell's broken.
Well, I mean,
it's functionally
I would
compromised.
suggest to you that every mutation ever seen that that we know about can be characterized as broken or bad in some way, but in another way they can all be characterized as good. So like, I mean, if you want to say that all the mutations are reductive and they're bad, but that somehow they're good at the same time, like, okay, the thing is that it's context dependent. Having more fur in a desert is bad. Having more fur in an Arctic is good. And if you had like an Arctic fox who found himself in a desert and his babies had a mutation,
but isn't that
it broke the hair and now they'd had less hair, you'd say, well, that's a breaking of a gene because he had more hair and now he has less hair. It just happens to be good for him.
I guess it depends if it's
first happened and they had a desert fox in the Arctic, and the desert fox had babies and the gene broke and now suddenly their hair is growing. You would say, well, that gene broke and that information was already there, but now the regulatory function has broken and now the hair is just growing out of control and it just happens to be good for that fox.
But that could just be the sorting out of genetic variability, where you have the allele.
Well, I'm talking about if there was a mutation.
Right. If there was a mutation, we'd have to look to each example and see. Like, for example, polar bears.
Well, these are two hypotheticals.
Right. Polar bears and their white fur, I do believe, is due to a damaged allele. But I think a lot of the cases when it comes to thick hair, short hair, long hair, whatever, dingoes versus wolves, so on and so forth. I think it's due to the sorting out of genetic variability where the allele is present for thick fur, let's say, but then you take all those thick fur dogs stick them into the deserts of Australia, while the variability for thick fur is lost. And so all that's left now is the variability for short fur. So I don't know if that you could consider that a mutation. It's just the sorting out of pre-existing.
Well, that's a loss of genetic diversity, right? But like,
right.
What I'm saying is that like I've never heard
as usual, as usual.
I've never heard a creationist ever say ever that any mutation was good ever, right? Like I've seen like evolutionists give examples of like nihilase. Nope, that's not good. Citrate. No, that's not good.
Because I think
nope, that's not good. Like they're all not good.
It's context dependent though. So it can be good in a very specific environment. Like for example, sickle cell anemia, we could talk about nihilase. I got a presentation on that, but for sake of time, sickle cell anemia, it is good But here's the thing. I don't want malaria. I also don't want sickle cell anemia. Sickle cell
Right.
anemia
I mean,
is
these
a
things have
disease that is.
costs and trade-offs sometimes, right?
The question
And
is
a
the
lot of
trade-off
times the
sustainable?
regulatory, like, all I'm saying is that all of the beneficial mutations, you can call them bad if you like. You can call them
like this.
broken. You can say they're bad if you want.
Mr. Anderson, let me say that. It's like, I find this funny because it's like, okay, and I'm sure you've heard me use this illustration before. If I temporarily wanted better gas mileage in my car, I could start removing weight, start removing the interior seats, remove the mirrors, just basically destroy the car. Well, temporarily, yeah, it's good. I got better gas mileage, and gas is really expensive these days. So that's a positive, right? But is that explaining how I built the car? Is that making the car any better? No, in the long run, I'm destroying the car. And that's why I like to point out that it's not necessary.
It depends, right? It's the context dependent.
If I start removing all those beautiful leather seats,
what?
If I start removing those beautiful leather seats from my car just to remove weight to get better gas mileage, we have a localized improvement, but in terms of total functionality, the car has degraded. It's been destroyed. And that's what we see with these examples is we have, like the citrate example with the E. coli, Lenski's experiment, we have localized improvements, localized increases of fitness, but because genotypically it's reductive and it's destroying pre-existing systems, overall it's a loss of total functionality. So there's no trade-off, I would argue.
That's pretty much what I expect to get, right? Is that there's no such thing in the creationist worldview. There is no such thing as a beneficial mutation. You cannot go up, no matter, you take any mutation you can think of. If you present it to a creationist as an example of an improvement, they will tell you it is not.
Time out real quick.
Let me just say this too. It could be a localized improvement. And you know what? Maybe it's more than a localized improvement. Maybe
not an overall improvement, right?
Maybe there's one that exists like that. But here's the thing. When you're climbing Mount Improbable, let's say I'm climbing up a mountain and I'm taking 20 steps backward, and then every 20 steps, let's just say, akin to a truly beneficial mutation that's not functionally compromising in any way. Now I take one step forward, but then another 20 steps backward, and then one step forward, another. You're never going to climb that mountain. And that's what we see is even if you did present 1,000 truly beneficial mutations that at the genotype, it's not reductive. It's never going to counterbalance the influx of low impact deleterious mutations pouring in. You're laughing because you're going to be a creationist in no time.
I'm laughing because I'm going to say that you're saying it's not going to counterbalance, and I'm going to say really what you're saying. Like, this is very much when I had Dr. Hovind, and I was like, admit to me that Tasmanian devils and venereal diseases are two different kinds of life, and he was like, I will not admit to that. I'm going to think about it.
Okay, I will admit
nothing counts.
Right now, show me right now a beneficial mutation. I'm not even saying they don't exist. Show me a beneficial mutation that is more than just a localized increase in fitness. I want to see an increase in total functionality.
I don't think one exists for you. That's my
Hey, time out. Let me ask.
Name one and I'll tell you.
I think we went from amoebas, or whatever, like he would call it amoebas, right? But like single-celled organisms to humans with all bad mutations.
Hey,
all of them were bad. All of them were reductions.
Mr. Anderson, let me point something out to you real quick. When you gave that characterization about creationist and beneficial mutations, you literally were stereotyping contra reality. Some creationists do absolutely hold to what you said, that all mutations are deleterious or there is no such thing as a beneficial mutation, but not all creationists actually think that.
Well, then I apologize. I apologize to all of the good creationists.
But Donny's point,
and all the bad ones too. I apologize to everybody.
Donny's point is still very relevant, though, because beneficial mutations can exist, and they can also be reductive simultaneously.
Sure.
And
they can be both good and bad at the same time.
And I mean, one of the points that I think you got to appreciate is the whole. how do I say this? The fixation problem, it's a real problem. So it's back to the waiting time problem. The whole theory of evolution, and this is one of the reasons that the whole genetic entropy argument from population genetics is just a bad mathematical model. It's because their argument against genetic entropy is identical to their argument for evolution over time. But let me ask you something real quick.
You lost me on that one.
Let me ask
you. Hey, T-Roy, is this what you're saying? Because now they want to make that no selection zone even smaller. Because, well, enough mutations amount to where now they are subject to selection. And so they're just nearly neutral, right?
Well, that was one of the other points I was going to make too, though, is because...
Yeah, because now that's fewer mutations drifting to fixation to help with forward evolution.
No, it's just that it's no.
Yes,
Donny, no. That you're missing.
You want to shrink that no selection zone.
What I'm saying is that as the population gets larger, the mutations which are selectable also increases, and so the mutations which drift to fixation,
if they're selectable, they're not subject to genetic drift, though.
Exactly.
Exactly.
So the ones that make it to fixation are closer and closer to neutral. Their deleteriousness
I just want to say
decreases as the population
you're undermining the whole basis of the molecular clock, because now you have fewer mutations reaching fixation because now they are under selection. But you need more mutations reaching fixation. But now they've gone from nearly neutral to, well, you call them nearly neutral because eventually they can be subject to selection, and so now they're not subject to drift. Now they're not going to drift to fixation.
Here's the solution to that problem. Just hang on, T-Rock. I got this one. Here's the solution to that problem. Do you remember you showed me a slide before and it said that the number of neutral mutations which are going to reach fixation is not going to be dependent upon population size, because as the population size increases, selection increases, but also the number of mutations which are introduced increases.
Right.
So the way that the neutral mutations, that there are still the same number of neutral mutations that reach fixation, even though selection is going to see a larger percentage of them, is that the number of neutral mutations which are introduced to the population will increase corresponding to the increase.
I would argue that those mutations that are reaching fixation are still slightly deleterious, and we could go down the route of junk DNA all day. And so if the majority of the genome is functional, then basically every single mutation is slightly deleterious, slightly harmful. And so all those mutations, even in light of what you're saying, that some are going to be subject to selection, they're still going to reach fixation, and that's irreversible and irreparable genetic damage. Is population wide, Mr. Mr. You come join the creationist side. Come here.
You know, I want to, but the problem is the math, right? The problem is that the probability. Look, for
2 + 2 is 4.
Look,
okay, go ahead.
The probability with respect to the ability of any particular mutation to reach fixation is going to be dependent upon the degree to which it is deleterious.
No, that's exactly the point.
I just have to ask this, and then you're next, T-Rock. I promise you're going to take over because I'm going to get a bite to eat anyways. Okay, last thing. Do you agree or disagree with Fatuma here?
No, I don't disagree with Fatuma. That is true. It's just that it only applies to truly neutral mutations.
Exactly. This is the whole point. You're trying to shrink that no selection zone.
Nearly neutral. Like, so 4NE is for neutral mutations. For nearly neutral mutations, you use this.
No, but the neutral, it's all nearly neutral.
Okay.
It's all nearly neutral. You're trying to shrink the no selection zone.
I'm not shrinking neutral. It. The population size is shrinking it.
No.
The fact that we have 7 billion people that these nearly neutral mutations have to make their way through before they reach fixation, they're not all going to have glorious mustaches.
Here's the question to answer all questions.
How many? That's the problem. Is you got?
Let me ask the question.
They all have glorious mustaches. But you got
Listen,
7 billion people.
I've been trying to grow a mustache for 34 years, and this is all I got.
Hey,
How many?
I'll help you out, Donnie. I got some good tips.
Josh is fine. Josh can have as many deleterious mutations as he wants. He's still going to have as many kids, right?
Right.
But the thing is, you got 7 billion people. They're not all going to be that gorgeous.
Here's going to answer. This is going to help the audience make their decision, okay, for tonight.
Well, I've made my decision.
How many of those mutations, 100 per person per generation, how many of those are nearly neutral as you're defining it?
I mean, it depends on I don't know. How many of them are nearly neutral?
And then the versus just strictly neutral. They have no harmful effects at all.
I don't know. Honestly, I don't know.
10?
Like, and you know what? No, like, so there's a whole like field, and people are. I don't think anybody actually knows. But
I know.
There's a thing called DFE, right? Distribution of fitness
effects, right?
Right. And I think they're still doing research to try and figure out exactly what that curve looks like.
But here's the thing.
And I don't know what it is.
I would argue that the function of the genome is roughly 60 to 80%. That means 60 to 80 of those mutations, the 100 mutations, are slightly deleterious. That's too much of a mutational load, even in light of everything you're saying, that in fixation equilibrium, that is going to increase the amount of slightly deleterious mutations that are hitting in the right way to become fixed. That's a lot of damage. You would need maybe one to be slightly deleterious to be nearly neutral. But if it's 60 or 80, would you agree that that's a pretty significant problem?
Maybe. I don't know. You know what? I'm hesitant to say that because I could then get caught out, and I don't know the answer, right? But maybe.
Okay. I'll just say this: people like Dan, Zach Hancock.
Yeah, I think there's something like I kind of remember that might be true.
Well, they'll say that the genome's about 10% functional.
Yeah,
and then
you
that
might
means
be right that number of like that if the genome is that functional, that would result in too many of the mutations being too deleterious. I'm not sure. I'm just not sure about that. You ask a real scientist.
You're doc. You've evolved from Mr. Anderson to Dr. Anderson. That M, you've experienced a single point mutation. It's gone from an M to a D, and this is good. You're the jack of all trades. And so, okay, we're gonna stop it right there.
That's very kind. You're kinder to me than I was to your friend Dr.
No matter how heated we get in the debate dojo, one of the rules of the debate dojo is that we shake hands at the end of the day.